This video is a step-by-step solution for the example entitled Determining Entropy Production in a Steam Turbine. In this example, you will learn about analyzing an expansion process for steam in a turbine at steady state. In this example, you will also learn to compute the rate at which entropy is produced within the turbine per kilogram of steam flowing. Let's look at the problem statement as given to us. Steam enters a turbine at a pressure of 30 bar, a temperature of 400 degrees C, and a velocity of 160 meters per second. Saturated vapor at 100 degrees C exits with a velocity of 100 meters per second. At steady state, the turbine develops work equal to 540 kilojoules per kilogram of steam flowing through the turbine. Heat transfer between the turbine and its surroundings occurs at an average outer surface temperature of 350 K. Determine the rate at which entropy is produced within the turbine per kilogram of steam flowing in kilojoules per kilogram Kelvin. Neglect the change in potential energy between the inlet and exit. First, let's do a critical read of the problem statement, highlighting in red the important information given and in green the information requested. Highlighted in red for the information provided, we have the following. Steam enters a turbine with a pressure of 30 bar, a temperature of 400 degrees C, and a velocity of 160 meters per second. Saturated vapor at 100 degrees C exits with a velocity of 100 meters per second. At steady state, the turbine develops work equal to 540 kilojoules per kilogram of steam flowing through the turbine. Heat transfer between the turbine and its surroundings occurs at the average outer temperature of 350 Kelvin. Also highlighted in red are the provided assumptions. Neglect the change in potential energy between the inlet and the exit. And highlighted in green for the requested information we have determine the rate at which entropy is produced within a turbine per kilogram of steam flowing in kilojoules per kilogram Kelvin. Let's start to develop the solution. The first thing to do with any problem solution is to summarize what is known. This is essentially the same information we highlighted in red in a critical read of the problem statement presented here in a compact bulleted list format. Steam expands through a turbine at steady state for which data are provided. The next thing to do is to summarize what we have to find. This is again the same information we highlighted in green in a critical read of the problem statement presented again in a bulleted list. Determine the rate of entropy production per kilogram of steam flowing. The next step in the solution is to develop a relevant schematic. In this case, it was provided to us. However, let's highlight a few important pieces of information that were provided, which will help us develop our solution. The first thing to note is there is mass entering and leaving the turbine. This immediately suggests that a control volume approach is the correct one. Having recognized this key fact, let's select a control volume boundary. In our case, it is selected to enclose the turbine and follows the physical boundary of the turbine as delineated on the schematic with a red dashed line. It ties in the turbine inlet condition at state 1, to the exit condition at state 2, to the work per unit mass produced, and the average temperature at which the stray heat transfer takes place between the turbines and the surroundings. The next step is to develop the appropriate thermodynamic diagram to represent the process. In this case, the TS diagram. Let's highlight the diagram with the information provided. State 1 is a superheated vapor state, and its pressure and temperature values are given to be P1 equal 30 bar and T1 equal 400 degrees C respectively. The process from 1 to 2 is an expansion process. The process is represented by a dashed line on the TS diagram until we reach state 2 at a lower pressure. State 2 is a saturated vapor state at a given temperature of 100 degrees C. Note that the entropy change is positive for this process. The next step is to develop an engineering model, which is a set of simplifying assumptions which will allow us to perform the analysis of the problem. The control volume shown in the diagram is at steady state. Heat transfer from the turbine to the surroundings occur at a specified average outer surface temperature, and the change in potential energy between the inlet and the exit can be neglected. Having completed all the initial steps in our solution and represented the process on a TS diagram, let's develop the rest of the analysis. In order to determine the entropy production per unit mass flowing through the turbine, we begin with applying the mass and entropy rate balances for the one inlet, one exit control volume at steady state. The mass balance equation is as follows. M1 dot is equal to M2 dot. And the entropy rate balance is written as 0 is equal to the sum of all the boundaries of Q dot divided by TB plus M1 dot times S1 minus M2 dot times S2 plus sigma dot. Since the heat transfer occurs only at one average temperature TB equals 350 Kelvin, the sum on the right-hand side of the entropy rate balance reduces simply to Q dot over TB. Combining the mass and entropy rate balance gives us 0 is equal to Q dot over TB plus M dot times S1 minus S2 plus sigma dot, where M dot is the mass flow rate through the turbine. Solving for the entropy production rate per unit mass gives us sigma dot over M dot is equal to minus Q dot over M dot divided by TB plus S1 minus S2. The heat transfer rate, Q dot over M dot, required by this expression for the entropy production is evaluated as follows. Combining the mass and energy rate balance and solving for the heat transfer yields the following. Q dot over M dot is equal to W dot over M dot plus H2 minus H1 plus V2 squared minus V1 squared over 2, where the potential energy change from inlet to exit was dropped from the energy rate balance by assumption 3. From the table of superheated steam at 30 bar and 400 degrees C, H1 is equal to 3230.9 kilojoules per kilogram, and from the saturation table for steam, H2 is equal to Hg at 100 degrees C equal to 2676.1 kilojoules per kilogram. Substituting those numerical values in the expression for the heat transfer gives us the following. Note the unit conversions from bar to pascals, or Newton per meter square, joules to kilojoules, to calculate the work per unit mass in kilojoules per kilogram. Evaluating the numerical expression above gives us the value of the heat transfer per unit mass. Q dot over M dot is equal to minus 22.6 kilojoules per kilogram. The minus sign indicates that the heat is being transferred out of the system, that is, an energy loss corresponding to the stray heat transfer from the turbine to the surroundings. From the saturation table, S2 is equal to 7.3549 kilojoules per kilogram Kelvin. And from the superheated steam table, S1 is equal to 6.9212 kilojoules per kilogram Kelvin. Substituting these values, as well as the value of the heat transfer which we just computed, and the given boundary temperature for this heat transfer, into the entropy rate balance equation, we obtain the following. Giving us a value for the entropy production per unit mass, sigma dot over M dot is equal to 0.498 kilojoules per kilogram Kelvin, which is the answer we were seeking. Quick quiz. If the boundary were located to include the turbine and a portion of the immediate surroundings, so heat transfer occurs at the temperature of the surroundings, 293 Kelvin, determine the rate at which entropy is produced within the enlarged control volume, in kilojoules per kilogram of steam flowing, keeping all other given data the same. You may want to pause the video at this point and perform the calculation to answer the question. The answer is 0.511 kilojoules per kilogram Kelvin. Hopefully you were successful in evaluating the correct answer. If not, review this video and all your calculations. If you are still not getting the correct answer, here are a few hints. The expression for the rate of entropy production is the same as before. Sigma dot over m dot is equal to minus q dot over m dot divided by Tb plus S1 minus S2. The properties at state 1 and 2 are unchanged within the larger control volume. However, the heat transfer, with the same magnitude, occurs across a boundary at a temperature Tb is equal to 293 Kelvin. The numerical evaluation of this expression with the new boundary temperature is left as an exercise. In closing, in this example we have learned about analyzing an expansion process for steam across a turbine at steady state. We have also learned how to compute the rate at which entropy is produced in the presence of straight heat transfer. This concludes the step-by-step solution of the example entitled Determining Entropy Production in a Steam Turbine.